Hello everyone. This is part 2 video on past year NEET questions from the chapter Thermal Properties of Matter in Physics. Now those who are looking at this video, right, can even take a look at the part 1 so that you will have continuity of questions. We'll start with a question that has come in the year 2014. This is a question based on the calorimetry. So all these calorimetry problems, right, they work on the principle of calorimetry, which is you'll have some hot objects, maybe one or two, and you'll have some cold objects, maybe one or two. It can be many also. Whatever is the heat lost by the hot object or hot objects will be equal to the heat gained by the cold object or cold objects if there are many. That is the principle of calorimetry. Okay. So we'll see what is happening in this question. Steam, which is at 100 degrees Celsius, is basically passed into 20 grams of water, which is at 10. So we have the vessel in which we have water, which is at 10, 20 grams of water. Steam is passed into it. What is the temperature of the steam? 100 degrees Celsius. When the water finally acquires a temperature of 80, means from 10, its temperature is increasing, means it must be gaining heat, right? So where is the heat coming from? It must be coming from the steam. When the water finally acquires a 80 degrees Celsius temperature, the mass of water present will be. So why are they saying mass of water? Don't we know that the mass of water is 20 grams? What must be happening? Because the passed steam, right, will condense. It will condense and then it will come to the final temperature. Whatever is the final temperature of the water that is there, whatever is the condensed steam will come to the same temperature. So as a result of which, right, some amount of mass will be added to this water, that let us say m. So m is the mass of the steam that is first getting condensed and then coming to that final temperature of 80. So if you look at the principle of calorimetry, right, let us see what is the heat lost by this m grams of steam. So first it is getting condensed, means look at the latent heat of vaporization for the steam. What is it? 540 calories per gram. Means what? For every 1 gram it is 540 calories, right? Here we have m grams, means what? M into 540. This will be in terms of calories. M is in grams, okay? And then once it is condensed, it will be like what? Water at 100. This is not staying at 100, it is coming to the final temperature of 80, means it is reducing its temperature. So it is losing heat. So what is the heat lost in coming down from 100 to 80? Mass, which is m, into specific heat capacity, which is 1, into it is coming from where? 100 to 80 it is coming, means what is the temperature drop? Temperature drop is 20, right? So totally what is it? M into 540 plus m into 20. This is what? M into 560. This is the total heat lost by that m grams of heat, steam, which is first getting condensed and then coming down from the temperature of 100 to temperature of 80. Okay, so this is on one side. Other side, what is there? The heat gained by the 20 grams of water. So what is that? So it is mass 20 into specific heat capacity is 1 into what is the temperature raise? From 10 it is becoming to 80, means what? Temperature raise is 70. So that is basically 1400. This is in terms of calories, by the way. So here also this is in terms of calories. And we should know whatever the m value we get, m will be in terms of what? Grams. So whatever the heat lost by the hot body is equal to heat gained by the cold body, right? That is the principle of calorimetry. Apply it, what we'll have? 1400, the heat gained by the cold body, which is the 20 grams of water in this case, is equal to what? Heat lost by the hot body, which is m into 560. So 10 56s, 10 140s. So m we require by, so 140 by 56. So we'll have 7 8s and 7 20s, 4 2s, 4 5s. That is what? Basically 5 by 2 means 2.5. It is in terms of grams. So this is that mass of the steam that is getting condensed and finally coming to that 80 degrees Celsius temperature. So they are asking what is the mass of water present means already there is 20 grams of water, which is raising the temperature from 10 to 80. In addition to that, we are getting what? 2.5 grams of the condensed steam that is coming to the final temperature of 80 degrees Celsius, which means what? The total mass of water at that particular temperature is what? 20 plus 2.5. How much it is? 22.5, which is our option D. Okay, so we have seen that there are quite a number of questions that have come based on the principle of calorimetry. Always the principle of calorimetry is what? Heat which is gained by the cold body or cold bodies will be equal to heat lost by the hot object or hot objects. Next we have a question that has come in the year 2014. This is based on Newton's law of cooling. A certain quantity of water cools from 70 to 60 in first 5 minutes. And 254 means, look at this. First step is what? From 70 it is coming to 60 in how much time? 5 minutes. And 254 means what? We are looking at 60 to 54. What is the time taken for that? 5 minutes. The temperature of the surrounding is, we need to find what is the temperature of the surrounding. So let us say temperature surrounding is what? Ts. What is the Newton's law of cooling concept? The average rate of cooling, which will be equal to what? A constant C into the temperature difference between the object and the surroundings. Average rate of cooling will be equal to what? A constant C into the temperature difference between the object and the surroundings. Here object temperature means since it is changing, we will take the average value. So 70 to 60 it is coming, means what is the average here? It is 70 plus 60 by 2, which is 65. Here 60 and 54. 60 and 54. The average is what? 60 plus 54 divided by 2, which is 57. That is the average here. Okay. So here what is the rate of cooling means? From 72 it is coming down to 60, means temperature drop is what? 10. Divided by time is what? 5 minutes. That is the rate of cooling. Here what is it? From 60 it is coming to 54, right? Rate of cooling means what? Temperature drop is 6 by 5 minutes. Okay, so look at it. First equation. We are going to get two equations. First equation is what? 10 by 5. Okay, is equal to what? C into average temperature is what? 65 minus Ts. Second equation is what? 6 by 5 is equal to C into average temperature is what? 57 minus Ts. So we have to keep one thing in mind. The temperature Ts here is going to come in which unit? Degree Celsius. Okay. So here what we can do? Maybe we can straight away divide the equations. Let us do equation 1 by equation 2, which means what? 5 minutes will be cancelled. Left hand side is what? 10 by C. Here C is also cancelled. 65 minus Ts by 57 minus Ts. That is the equation. Now we have to get the Ts value, right? Temperature of surroundings. So that's it. So it's a very straightforward question based on the use of the Newton's law of cooling. Okay, the only thing is we should have a little bit patience to conclude the step and then get the final answer. Now what we have to be doing here, we should just simply cross multiply. If you cross multiply, what is going to happen? Cross multiply. So this side is what? 10 into 57 means 570 minus 10 into Ts is equal to what? 65 into 6. So what is 65 into 6? 6 5s are 30, 6 6 are 36, means 390. Okay, minus 6 Ts. So we will bring the minus 10 Ts to the left side and take it to the right. So rearrange them. What we'll have? 570 minus 390 is equal to what? Already minus 6 Ts is there plus 10 Ts. Totally what is it? 4 Ts. What is 570 minus 390? This is 180 is equal to what? 4 times Ts, means 180 by 4. That is what? 45. As we said, the temperature will be in what? Celsius scale. So what is the temperature of the surroundings? It is what? 45 degrees Celsius. So just we have written the average rate of cooling expression in both the cases, and from there onwards it is just like how do we solve. And whenever we can remember this, whenever we have these two cases, case 1 case 2 kind of situation in the Newton's law problem, right, always it will be like, we'll divide the equation so that C will get cancelled, because C is a constant which is unknown to us. It's a constant nevertheless. So usually it will be like what, we'll divide it and thereby the C will get cancelled, and we will be able to find out whatever is the information that is being asked. Next we have a theoretical question. This has come in the 2013 paper NEET. A piece of iron is heated in a flame. Basically we are heating it. It first becomes dull red, then becomes reddish yellow, and finally turns into white hot. The correct explanation for the above observation is possible by using, see, what is the dull red, reddish yellow, and finally turning into white. Basically what we are talking about is the color of the radiation that is emitted. Okay, so color will correspond to what? It will correspond to the wavelength. Color will correspond to what? Wavelength. So if you look at the visible region, right, so what do we have? We have all these, violet, indigo, blue, green, yellow, orange, red. So this is the spectrum. So here if you look at the lambda, right, as we go from left to right, it is what? Increasing. So when we say red means what? High wavelength. Yellow means lower wavelength. Now the Wien's displacement law for the energy emitted by a black body, particularly the relation is what? Lambda m into T will be equal to a constant which we call as the Wien's constant B. So what we see is that the lambda m basically corresponds to the wavelength. It will correspond to wavelength through which maximum intensity of the radiation is emitted. Through which maximum intensity of the radiation is basically emitted. Means most of the energy is coming through that particular wavelength. And that is what we will be able to see predominantly. So initially what is happening? Low temperature. So when you are just heating that iron, so think about it, there is a furnace. Okay, there is a furnace. We are keeping that iron rod into the furnace. Okay. Initially what is going to happen? We'll have low temperature. Look at this relation. Temperature low means what? Lambda will be high, because lambda m into T will be constant. Lambda high means what? We'll see predominantly red. As temperature is increasing means what? Lambda will decrease. So we'll come to yellow, and then we'll see mix of these colors, isn't it? So what is it correlated by? It is basically correlated by what? The Wien's displacement law, which is whenever an object is radiating, the wavelength through which maximum intensity radiation is coming, that is what we call as lambda m. So lambda m into temperature of the body will be what? Constant. The constant is called as Wien's constant. The value of the constant is 2.898 into 10 power minus 3 meter into Kelvin. So the value is not required here, but just to have an idea. Okay. In fact, we see that we got quite a number of questions based on the Wien's displacement law in this past year papers. Okay, so we'll see that those questions also we will discuss as we go along. So in the other part videos, right, we'll see some more questions based on the Wien's displacement law. Next we have a question that has come in the Karnataka paper 2013. This is based on the conduction. Two metal rods 1 and 2 having same length and same temperature difference. They have the same length and same temperature difference across the ends. Their thermal conductivities are K1 and K2. What are the thermal conductivities? One is having a thermal conductivity K1, other is having a thermal conductivity K2. And cross section areas are A1 and A2. If the rate of heat conduction in one is 4 times that in 2, means what? The rate of heat conduction. Remember, if you have any conducting rod, if there is a conducting rod, okay, through that conducting rod, what is the rate of heat conduction given by? If you have a conducting rod of length say L, area of cross section A, temperature difference delta T, then the and thermal conductivity K, then the rate of conduction, right, So rate of conduction is going to be what? It will be equal to Ka by L into delta T. So this is a very standard relation for the rate of conduction of heat. Okay, so through the particular rod. Okay, now here we have a comparison. So we have a rod 1 and rod 2. So look at it. So we have the rod 1 and rod 2. So we'll just list down whatever is the given information. So this is the rod 1 and this is the rod 2. What is the given information? They have the same length, means L is same, and same temperature difference, delta T is also same. Okay, one of them is having thermal conductivity K1, other is having K2. Whatever is the area here, A2, A1, A2 are the areas. So here what is the formula for the rate of conduction of heat? It is what? K1 A1 by L into delta T. So they are saying the rate of conduction in rod 1 is 4 times, means it is 4 times. What is the rate of conduction in the rod 2? K2 A2 by L into delta T. So here we can see L is cancelled, delta T is also cancelled. So what do we have? K1 A1 is simply equal to what? 4 times of K2 A2. That's it. This is the relation. They are asking us what? What is the given relation that will satisfy? What is it? K1 A1 will be equal to what? 4 times of K2 A2. All that we are doing is separately writing down the rate of conduction expression and relating them by whatever the relation they have talked about. What is the relation they have talked about? In that rod 1, the rate of conduction is what? 4 times that of the rate of conduction in the rod 2. That is the relation we have represented. Okay. We'll move on to the next question. This is a question that has come in the year 2012. This is based on the radiation law or the Stephen's law. If the radius of a star is R and it acts as a black body, what would be the temperature of the star in which the rate of energy production is Q? Means, here this Q is basically what? Rate of energy production, means this is what we will generally call as the radiation power. So we have the star which is having a radius R, means we are considering the star to be like a sphere. Radius is what? R. Means the outer surface area is what? What will be the outer surface area? It is 4 pi R square. Okay. Through this area the radiation is being emitted out. Now the Stephen's law is what? Radiation power, in this case that is Q. Radiation power of a black body, we are considering it like a black body, is equal to what? Sigma, Stephen's constant, into area of that particular object into absolute temperature power 4. Okay, so here sigma area is what? 4 pi capital R square into T power 4. They are asking us the temperature, right? Means what? Let us bring everything to the left side. What we'll have? Q by 4 pi R square into sigma is equal to what? T power 4. Means we have to take a fourth root on both sides. Means what is going to happen? T will be equal to what? Q by 4 pi R square into sigma whole power 1 by 4 will come. So what is the correct answer for this? It's a straight question, just formula based question on the Stephen's law. So what is the option for this? It is option D. Next we have a question that has come in the year 2012, and this is based on the idea of heat given to a body relation to the temperature change. So normally what happens whenever we look at any object, let's say there is an object, it can have any shape, need not be like a a rod or anything, it can be having any shape. When we give heat to the object, it will use the heat to increase the temperature. So what is the relation? Q is equal to ms delta T. So we'll see that the temperature rise and Q will be having a linear relation. There will be what? There will be a linear relation between the temperature and the heat given. But the thing is, whenever there is a phase change, during phase change what is going to happen? Like typically if you look at say, let's talk about water itself. Water will start at minus 20 degrees Celsius, which is in the form of solid ice. If you supply, this is the heat given and this is the temperature change. So heat given can also be measured by the time for which we are supplying the heat. Okay, so we look at initially what is going to happen. We'll supply heat and we'll see that their temperature will be increasing in a linear relation until it comes to 0. 0, what is going to happen? Some amount of heat will be absorbed, but temperature will not rise. We call it as what? Latent heat of fusion. Then again the temperature will start increasing till it reaches this 100 degrees Celsius. At that 100 again, temperature will remain constant for some time till it is absorbing the latent heat of vaporization, and then again it will start increasing. So this is what we will see, the temperature change with regard to the heat supplied or the time for which the heat is supplied. So wherever we have a phase change, we will see that the line will be horizontal. Now the question is exactly based on the same idea. Liquid oxygen means initially it is in which state? Liquid state. At 50 Kelvin is heated to 300 Kelvin. At constant pressure of 1 atm, the rate of heating is constant. Rate of heating is constant means what? Heat that is given will be equal to what? Rate of heating into the time. So we'll see that the total heat given will depend upon the time. More time means more heat is given, like that. Which one of the following graphs represents the variation of temperature with time? So here oxygen is already in the liquid state. At what temperature? 50 Kelvin. Now what happens is, if the oxygen remains as a liquid from 50 to 300, what is it that we'll expect? We'll expect that it will be like a linear relation. But this is not going to happen. What will be occurring is, the oxygen will have a phase change where at nearly 90 Kelvin, the liquid oxygen will convert itself into gaseous state. Means, look at this graph A. From, say for example, the 50 Kelvin to 90 Kelvin, you will have a linear relation. Then at 90 Kelvin, you will have horizontal line for some time. What is it? That is corresponding to the latent heat. Then again the temperature is going to increase linearly. Okay, so what is the correct graph that represents the behavior? It is what? Option A. It is not, the non-linear relation will not be there, because look at this, this is what? Q is equal to ms delta T, right? The relation will be what? Linear relation. So this is what? Delta T means m into s into T final minus T initial. You will see that the relation is what? It will be a linear relation between the heat given and the final temperature. So what is the correct answer for this? Option A. Why? Because in between at around 90 Kelvin we have a phase change. The oxygen is becoming oxygen gas. After that there will be no more phase change, right? So from 90 Kelvin up to 300 Kelvin, it will still keep increasing its temperature. That's it. We'll move on to the next question. This is a question based on the thermal conduction. A slab of stone, what is the area? 0.36 meter square and thickness 0.1 meter, is exposed on the lower surface to the steam at 100. The lower surface of that slab is exposed to what? Steam, which is at 100. A block of ice at 0 degrees Celsius is resting on the upper surface of the slab. So we can just visualize it like this. This is the slab. This slab. Below is what? Steam. On the above we are keeping ice, which is at 0 degrees Celsius. What is going to happen here? Look at it. So this end is maintained at 100, that end is maintained at what? 0. Means we will see that there will be thermal conduction through the slab. What is the area of cross section? 0.36 meter square. What is the length here? 0.1. In 1 hour time, 1 hour means what? It will be 3600 seconds, since we are talking about everything in the SI system of units. Okay, in 1 hour time 4.8 kg of ice is melted. In 1 hour time 4.8 kg of the ice is basically melted. The thermal conductivity of the slab is, so we have to find what is the thermal conductivity K of the slab. Given information is what? Latent heat of fusion for the ice is what? In terms of SI unit, what is it? 3.36 into 10 power 5 joule per kg. So what is it that we are going to do? Whatever the heat that is supplied through conduction is taken by the ice, and the ice is simply melting. So what is the principle we are going to use? heat that is going through conduction is spent in melting of the ice. Okay, so we look at the total heat that will go through conduction is what? The rate of conduction is what? Ka into T1 minus T2 by L. This is the rate of conduction into time. We have to multiply by time. That will give us what? The total heat that is going through that slab because of the conduction. So T1 here is what? This is 100. T2 is what? 0. K is unknown. A is here. L is also here. L is this one. The length. So this is the length across which the conduction is happening. Time is what? Already we have 3600 seconds. Let us substitute. So K into 0.36 into 100 minus 0 into 3600 by 0.1. Everything is in the SI system of unit. Everything here is in the SI system of unit. Okay, so this is the Q value, the heat that is supplied through conduction. And this must be equal to the heat that is needed to melt the ice. So 4.8 kg of ice, right? What is the latent heat? 3.36 into 10 power 5 joule per kg. So which means what? The heat that is required for the melting of ice is what? Mass of the ice into latent heat. 4.8 into 3.36 into 10 power 5. So this heat is being supplied by what? Conduction. No. So both must be same. Equate them. What we'll have? K into 0.36 into 100 minus 0 means 100 only. Into 3600 by 0.1 is equal to what? 4.8 into 3.36 into 10 power 5. So here we can see some cancellation. What will be the cancellation? 0.1 means 10 power minus 1. That will go to the numerator as what? 10. Here this is like what? 36 into 10 square. This is like what? 10 square. Totally 10 square into 10 square into 10. 10 power 5. So this 10 power 5 will be cancelled as it is. Now we are looking for the K value, right? So K will be equal to what? K will be equal to 4.8 into 3.36 divided by 0.36 into 36. Okay, so this is what we have to be simplifying. So if we simplify this, right, we'll get the answer close to as what? 1.24. So this requires a little bit of calculation. The idea is straightforward. Whatever the heat that is coming through conduction is equal to what? The heat that is required for the melting of the ice. That is the concept. So the final answer also will be coming in the SI system of unit. Okay. We'll move on to the next question. This is a question again based on the conduction. A cylindrical metallic rod in thermal contact with two reservoirs of heat at its two ends conducts an amount of heat Q in a time t. Means, initially the rate of conduction will be what? Q by T, because heat that is supplied is Q in the time T. The metallic rod is melted and the material is formed into a rod of half the radius of the original rod. Means, look at it. The original rod is having a radius is R and length is L. This is melted and we are forming a rod which is having half the radius. What is going to happen? When the radius is half, it's what? R by 2. So we must notice one thing. Same material, right? Volume must remain constant. Volume must be remaining constant, which means what? Here what is the volume? Area of cross section into length. Here what is the volume? Area of cross section into length, let us say L dash. So both volumes must be same, right? Which means what? So we'll have a relation. What is it? Pi into R square by 4 into L dash is equal to what? Pi R square into L. So pi R square is cancelled. So L dash is equal to what? 4L, which means after melting we are casting it into another rod of radius R by 2, right? What will be the length of that? It will be 4 times the original length. How are we getting it? We are getting it by looking at the same material, right? Volume must remain constant. Okay. So this is the second. So this is the first case, this is second case. Okay. Now what is the amount of the heat conducted by the new rod when placed in thermal contact with the same two reservoirs? So in the first case, right, what is the rate of conduction, this is Q by T, which is equal to what? Let's say thermal conductivity is K. It's a property of the material. It will be same. K into area of cross section. Here is what? Pi r square into temperature difference between the ends is delta T divided by L. Second case, let's say the heat that is going is Q dash in the same amount of time T. So Q dash by T is equal to what? Thermal conductivity will not change. Here what is the area? It is what? Area will be pi into r square by 4 into delta T divided by what is the length here? It is 4L. So we can see here clearly, just bring the factors outside. This is 1 by 4, already there is a 4 in the denominator. Totally what do we have? 1 by 16. 1 by 16 into K into pi r square delta T by L. What is K into pi r square delta T by L? Look at this. Q by T, right? Which means what? Q dash by T is equal to 1 by 16 into Q by T. Means what? Q dash is equal to what? Q by 16. So in the second case, what is the amount of the heat that will flow? It will be 1 by 16th of the original heat, which is what? 1 by 16th of Q. So the correct answer for this is option B. So here the thing is what? How do we relate the first rod and the second rod? For both of them, thermal conductivity K value is not changing because the material is not changing. Temperature difference between the ends is not changing because second case also what they are saying, we are keeping the rods across the same reservoirs. Means one side the temperature is, let us say T1, other side is T2. That is going to remain the same. So delta T also will remain the same. What is changing? Area of cross section is changing, length is changing. So this is about the part 2 video, and we'll see in the next part video.